Swayam Prabha. Digital India. Educated India.
Hello all. So welcome to the Astrochemistry course, and today we will be discussing lecture 11. Now, so far in this course, we've had 10 30-minute lectures, correct? And as part of the 10 30-minute lectures, we've introduced cell-level concepts. For example, we started off with how the area of astrochemistry can be connected with astrobiology and astrophysics, and I provided a glimpse of why astrochemistry is important and how it could teach us various aspects about chemistry happening in space versus what's happening on Earth. This was followed by an introduction to the way in which lighter elements were formed from the Big Bang theory itself, right? The Big Bang nucleosynthesis. And then we understood how, from the circumstellar disk of what is called as a protostar, we can have the formation of planets, asteroids, and comets, each of which presents its own variation in chemistry. And we then got introduced to the idea of the interstellar medium and saw the differences between the interstellar medium and Earth, especially from the point of view of what chemistry can happen. So having introduced this many concepts, right, time is now ripe for what is called as a tutorial session. This is of course lecture 11, but this is going to be the first tutorial session. Now, what is a tutorial session? I mean, in lectures, we shall be, it's more or less a monologue, right? I mean, of course, there will be some interaction if the students interact, but it's mostly a monologue where, I keep adding more and more concepts to your knowledge base. In the tutorials, we shall be solving some problems based on these lectures that were covered. Okay, right? So the problems will be such that they reinforce your basic concepts of not only astrochemistry, but also the connecting physics, physical chemistry, organic chemistry, and inorganic chemistry. All right. After all, this is astrochemistry. It's an applied science, right? So the applied science has its base firmly in physics and chemistry. So the connect between, the basics of physics and chemistry to solve astrochemical problems of interest, they will be brought about in the problem solving sessions in this tutorial. Is that clear? And roughly, we shall have like one tutorial, roughly, per like 2.5 or 3 lectures. Okay, this is to ensure that the problems from any particular concept, they are all introduced to you right at an early stage, instead of having a cumulative lecture series and then having the problem solving sessions, so that if at all any questions arise, they can all be sorted then and there. Okay, so on that note, the next 4 30-minute lectures, that is lectures 11, 12, 13, and 14, will be tutorial sessions. We'll be having 4 tutorial sessions for the net 10 lectures that we had. Is that clear? Also, what we shall be doing is, I mean, this is an approximate number. It is not necessary that we shall be following this in a sacrosanct way. The idea being that the tutorial sessions will be held once enough concepts are introduced and we have enough to solve problems from. Okay, that's it. And again, I want to write this explicitly. In the tutorials, we shall explicitly, okay, right, see the connect between astrochemistry which is an applied science, and the basics of physics, physical chemistry, inorganic chemistry, and organic chemistry. So the key is that in any applied science, if you want to understand the applied science well enough, you must have a thorough understanding of the fundamentals of the basics, which in this case are physics and chemistry by and large. Are we all good? Okay, so on that note, we shall begin our tutorial session. So how will the tutorial session work? I shall be giving you problems. I shall be writing down the questions on the board. Shall give you some time to mull over the answers, and we can then discuss the answers and questions and answers. So the first question in this tutorial 1 is going to be, let's start with simple questions, okay, to just get some warm up. Let's have some true or false type questions. Okay, this will reinforce whether the concepts that were taught in the lectures, they have actually reached the students in a good way. Okay, so we'll be discussing some true or false type questions, and along with giving the right reasons with the explanations. So this is the first question. Okay, and so 1A, the very first question, in this category, it's a simple warm-up. So we call the very first or the second lecture in the series. So Chandrayaan 3, right? That is what concluded most recently in 2023. Okay, so Chandrayaan 3 discovered the mission. Okay, as part of Chandrayaan 3 led us to the discovery of water in moon. So what is the answer? Is it true or false? And if true, why? If false, why? It's just a warm-up question. It's a reasonably easy question, but nonetheless, it will tell you how important astrochemistry is. And even though, physicists and engineers send all these spacecrafts and rockets to outer space, it is one major aim of those exercises is to understand the chemical composition of these celestial bodies. So what is the answer? The answer is, it's false. The answer is actually that it is not Chandrayaan 3. I'll just call it like C3, but it was C1 way back, I think in 2008 or 2009. Okay, right? So Chandrayaan 1, this is kind of a factual general knowledge type question. We're just warming into the tutorial. So if it was too easy, okay, right, don't mind it. So the answer is false. It was Chandrayaan 1 that led to discovery of water. And in C2, we had the discovery of water and some hydroxyl radical, I believe. Okay. And in Chandrayaan 3, we, if I'm correct, okay, we had noticed the discovery of sulfur containing species, sulfur in the south pole of moon. Of the moon, of course, okay. So it is not Chandrayaan 3, but Chandrayaan 1 itself. And why am I especially highlighting this specific point? It is because the discovery of water on the moon was first made by Chandrayaan 1, which is an Indian organization, which is an Indian mission, right? So it was ISRO and Chandrayaan 1 who first discovered water on moon. I want you folks to remember and note this point in particular. Okay? All right. So let us now go to the next question. At low temperatures in the keto-enol tautomerism of acetaldehyde. This is the molecule. Okay, acetaldehyde. This is acetaldehyde. The keto form predominates. What is the answer? Well, to answer this question, you should know what is keto, what is enol, right? And you must also know what are we talking about and why is it relevant to astrochemistry? Okay, but we discussed all of this in the very first lecture. So I just want to highlight it and emphasize that chemistry is going to be a recurring theme. The basics of chemistry are going to be a recurring theme in this course. Okay, so what is the answer here? The answer is that it's false. Correct. It is false because it is not the keto. It is not the keto form, but it is rather the enol form predominates, which predominates. Okay, let's just see why. I mean, I've already told you some reason, but I shall further emphasize here. So in page 5, yeah. So what is the keto-enol tautomeranism that we are talking about? We are talking about this equilibrium. This, it's better written as this, right? And then this hydrogen goes over there. We have so this is the keto form and this is the enol form. Now, if you recall in the very first lecture in this astrochemistry course, or maybe the second lecture, okay, I had told you folks that now at room temperature, which is approximately 300 Kelvin and 1 atm, this form predominates. This form predominates. Why is that? It is because in the same carbon, having a double bond and OH group together, right? That is going to be a highly unstable situation because the electron density in the vicinity of this carbon is very high, and overall due to electronic repulsion, this form is not going to be so stable. But if you recall, the question says what? At low temperature, especially if we consider space type conditions such as like molecular clouds type condition at low temperature and very low pressures especially, right? The fact, that even this entity could be stabilized. And what is the reason? The reason is that the overall kinetic energy of the molecule is going to be so low because we're talking about the temperature being very low, okay, right? And therefore, at low temperature, with overall kinetic energy being very low, enol form could well predominate, and it does predominate in this case. Predominates. Dominates. I'll just write it as. Okay, so that's the whole point. So why is this question relevant in the context of space? It is important because the conditions on Earth can lead to the dominance of one particular isomer or molecule, right? Whereas under the conditions prevalent in space, some other form could be dominant. So the chemistry of space could be complementary to what is happening on Earth. So that is the relevance of this question. Okay, we'll move on to the next question now. The next question is going to be that C. What is the answer? I mean, this is more or less a fact-based question. If you recall the equation I had given in the very first lecture, the answer would be straightforward. The answer is, of course, it's true. We also highlighted this specific behavior of H2, right? When it reacts with a species such as H2 plus, highly reactive, plus H2 giving H3 plus H. So here this acts as the acid and this species H2 acts as a base. And what did this reaction highlight to us about interstellar chemistry? It is that molecules can behave in unexpected ways in the interstellar medium vis-a-vis what is known as Earth. For example, for a molecule to behave as a base we need some electronegative atom and some entity that would love to grab a proton, according to the Lowry-Bronsted definition of acid-base chemistry, correct? But in the interstellar medium, the fact that H2 plus is a very highly reactive species, so it can act as an acid, and so H2, without having any lone pair of electrons, is able to abstract a proton from H2 plus to form H3 plus, and leaving this guy to be H alone. So very different acid-base chemistry is possible in the interstellar medium. Okay, we'll now move on to the next question. D. The question is, observation of blue shifted starlight from a galaxy. Okay. Implies that the galaxy is moving towards us. So this is the statement. And is it true or false, and why? Straightforward, right? The answer is, of course, it's false. The fact that, now what concept does this question connect to? This question connects us with the idea of Hubble's idea that the universe is expanding. And so when the universe is more or less expanding, what happens? Well, the actual wavelength is greater than the wavelength noted, assuming that the galaxy, the star and then the galaxy would be at rest, right? Now, when it is greater, we call that redshift. Okay. Oh, this is actually true. My apologies. Okay. Or I would just change the question. Is moving away from us. I'll clarify the confusion in just a minute. So the fact is that when based on the idea of relative motion, okay, just like in sound waves, we saw that when the galaxy is actually moving away from us, the wavelength should be higher, correct? And when the galaxy is moving towards us, the wavelength should be lower. And when the wavelength is higher, what do we call it? Do we call it red shifted or blue shifted? That is where the whole thing is. We call it red shifted, correct? So lambda moving greater than lambda rest, we call it red shifted, and lambda rest greater than lambda moving, that is blue shifted. What is the reason behind it? It follows the order of the energies of the red and the blue lines, right? The ultraviolet region is more energetic. It has a lower wavelength. E equals hc over lambda. Please recollect it. Okay. So if it is red shifted, the galaxy is therefore moving away from us. So what does this statement say? Observation of blue shifted starlight implies that the galaxy is moving away from us, which is obviously false. If I make it as red shifted, then the statement would be true. Are we all good? And my apologies about this initial hiccup, where I thought I had misread the question myself. Are we clear now? So the idea is that if it is red shifted, the galaxy is moving away from us. And if it is blue shifted, the galaxy is moving towards us. It follows the very same idea of the Doppler effect. In fact, in this tutorial or the next session, we shall be solving some more problems related to this. Okay? Yeah. On that note, we'll move on to the next question. And this will be question E. It can be said that, in general, comets contain molecules which are bound weaker interactions than the molecules in an asteroid? What is the answer? We have went through this part in great detail a few lectures ago, right? The answer is, of course, it is true. Why is that? Because the comets contain several volatile organic and small inorganic molecules, whereas as far as the asteroids are concerned, they are formed by giant lattices of strongly bound inorganic molecules binding together, right? So that is why the comets, we have the formation of what are called as ices, whereas in the asteroids and the meteorites, we have what is called as the formation of rocks. And asteroids in general are rocky, whereas comets are icy. And that's also why, if we recall, the comets appear to be a fuzzy point when visualized through a telescope, whereas the asteroids appear to be, a firm point. So do you recall this difference? Okay. So we now move to the next question here. So the question is that the statement, I'm just writing down the statement now. It is that the number density in the ISM is low with respect to Earth. If you consider any region, we don't specifically talk about any one particular region, but for all the regions, so far this statement is true, right? Yeah, because the ISM of the interstellar medium contains highly unstable species. For example, you can talk about what's an unstable species you could think of that we noticed in space. We already saw, right? For example, H2 plus and something like H3 plus, etc. Right? These are just some examples. So, what is the answer? Come to think of it, the whole statement kind of makes sense, right? In the sense that, when the number density is actually very low, right? When the number density is very low, it could be because any molecule that is formed reacts so fast because they are so highly reactive, and overall nothing is left over there. Is that what is happening here? Take a moment and think about the answer. So what is the answer? The answer is, yeah, so some people could be arguing that, well, this is of course true, because like I just rationalized myself a few moments ago, that hey, eventually, because there are lots of highly unstable species, the examples of which we have already given here, right, the number density will be low eventually. That is one side of the argument. What about the counter argument? There are only two possible answers, right? True or false. So we've argued for why it should be true. What about the false section? What about the false idea? Well, it is false, one could argue, based on the logic that, hey, recall from our previous lectures that we discussed about the time scale of interstellar reactions. What is the time scale? It is of the order of 10 to the power 6 or 10 to the power 7 years, right? That is how long it takes for an interstellar reaction to be over. So therefore, it's not a question of reactivity that leads to the number density being low. What else could be that? It is actually the absence of molecules itself, right? It is the actual absence of molecules, given that the space, the dimensions of any molecular cloud or the ISM itself is so huge. We're talking about, what are the units employed? Light years, or like parsecs, right? Which is all many 10 to the power close to 9 or 10 kilometers, in that range, right? So we're talking about exceptionally large distances and very few molecules sticking around. So what is the answer? Yeah, the second one makes more sense. So it is of course false, and it is because in the first place, so few molecules are present. Okay, so it has got nothing to do with highly unstable or highly unreactive molecules. It is not like they were highly unstable species, they readily form and then they react immediately. No, it is that the number density is low because in the first place there is nothing over there. There is almost nothing over there. So that is the logical part for this answer. Okay, so we'll look at the last true or false question, which is that the ISM, more or less a continuation, you can call it a supplement to this question. The ISM contains many species which are highly unstable and reactive on Earth. For example, the same examples that we saw in the last question, H2 plus and H3 plus. Yeah, I can hear that the answer is of course going to be true, but we'll elaborate. We'll elaborate a concept based on this. You have something like H minus, you have something like OH plus, you have something like OH radical, you also have something like Cn minus, etc., etc. I'm just giving some examples of cations and anions and free radicals also. The answer is of course true, but I want to highlight an important chemical principle based on it. It is that why are these unstable species then even present in the ISM? As I have been telling you in the lectures repeatedly, in fact, okay, the reason why several of these highly unstable species, as we understand about their stability or instability on Earth, they could be present in the ISM because of the reason that it is the conditions that determine the conditions determine the stability or instability of a molecule, correct? So in the ISM, and what do I mean by condition? By condition, I'm talking about a combination of pressure and temperature, because the pressure and temperature in the ISM are so different, are so very different from what is observed on Earth, right? The conventional ideas of stability and instability do not apply to molecules in space, and that is why some very exotic molecules such as H minus OH plus, once they form, they can get formed by the bombardment of, for example, an electron onto an H atom, right, in space. Once formed, even these stable, they stay unreactive in space for a long time because the number density is also low. All right. So the answer is that P and T different in Earth than ISM. Okay. So far in this tutorial, we have looked into a series of true or false type questions. We shall continue in the next lecture, which shall be lecture 12 and tutorial 2, with more such questions to follow. Thank you so much.